This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to continue our study of heat, and specifically here we'll talk about the concept of latent heat, heat of fusion, and heat of vaporization. In our previous video, we talked about heat, and we said that heat is the transfer of thermal energy. So it's energy in motion from one object to another. Remember that thermal energy is the total amount of potential and kinetic energy of all the atoms and the molecules that make up the substance. In our last video, we also discussed how much heat is required to raise the temperature of an object, or how much heat needs to be lost to lower the temperature of an object by a certain amount, delta T. Let's just review the units here. We're generally using joules as our unit of energy, and for mass we're using the unit of kilograms. Temperature we know is in degrees Celsius, and so that's why the units for the specific heat capacity have to be in joules per kilogram degree Celsius, because that way when we look at those units on the right, everything cancels out except joules. We know that an equation always has to have the same units on either side. I just want to note that a lot of problems involving heat often use calories instead of joules, and we talked about the unit of the calorie in our last video as well. But if we were to rewrite that equation, Q equals mc delta T, often you would find that calories would be used as the unit for heat. Oftentimes, instead of kilograms, grams are used. Temperature is almost always in degrees Celsius, and so notice that what that means is the units for specific heat capacity in that case would need to be calories per gram degree C. And so if you look up the specific heat capacity of a material on the internet, you have to watch out for what units it's in. So it could be in joules per kilogram degree Celsius, could be in calories per gram degree Celsius. Okay, well, let's start looking at some new information. Let's say that we have the following scenario. You start with a glass filled with water and ice and bring it outside on a warm day. So you can see we've got the sun up there in the corner. You constantly stir the ice with a thermometer and periodically record the temperature as the ice melts. What will your reading show? So think about this for a minute. What do you think the reading on the thermometer will do as that ice melts in the water? Well, it turns out that what you'll see if you actually do this is that as long as there's any ice left in the water, the temperature remains at 0 degrees Celsius. So as time goes on, and you'll notice we're graphing temperature versus time, as time goes on, the temperature stays the same, and it only starts to increase from 0 once all of the ice is gone. What that tells us is that it takes energy to cause a phase change, to go from, in this case, the solid phase to the liquid phase. And so during this time, all of the energy that is being absorbed by that ice-water mixture is simply going into changing ice to liquid, and none of it is going into changing the temperature of the liquid and ice mixture. So what we learn then is that energy is required to change the phase of a material. So if we want to go from solid to liquid, or we want to go to liquid, from liquid to gas, we have to add heat. And we're all familiar with this idea with water. We know if we start with ice and we put it in a pan and turn the stove on, we can melt that to a liquid. If we keep going, we can turn it into a gas. Of course, the process also works in the reverse, we can take a gas and turn it into a liquid or a liquid into a solid, but in that case we need to remove heat. Okay, well let's look at the following experiment. So we're going to do a heating experiment with water. Let's say that we start with ice at a temperature below 0 degrees, and we slowly add heat, and we look at what happens. Well, at first, if we start with ice at some temperature below 0, then the first thing we have to do is just get that ice up to the freezing temperature. And so as we add heat, we actually change the temperature of the ice, but then the heat that we add during this phase is solely going into changing the ice from a solid to a liquid. Once all of the ice has been turned into a liquid, now we can raise the temperature of that liquid by adding more heat. Then once again we get to another plateau. This is where we're changing the water into steam or gas. And so again, all the energy that's being added here is just to accomplish that phase change. So we're going to define a couple new terms here. What we call the heat of fusion, or sometimes is called the latent heat of fusion. We'll talk more about that in a minute. The heat of fusion is the amount of energy required to change 1 kilogram of a substance from a solid to a liquid. So in other words, that's what is important in this phase. How much energy does it take to do that phase change? We also have the heat of vaporization, and that's simply the amount of energy required to take 1 kilogram of the substance and now change it from a liquid to a solid. And so when we're looking at changing the phase, we need to either know the heat of fusion or the heat of vaporization of the material. Let's talk about this term latent heat. Latent means hidden. And so when we use the term latent heat, we mean that's sort of a more general term that could be referring to either heat of vaporization or heat of fusion. So usually I'm just going to say heat of fusion or heat of vaporization, but again you can say latent heat of fusion or latent heat of vaporization, latent heat being a term to mean both. Why do we call it latent? Well, normally we're used to the idea that if we add heat to a material, the temperature raises. You'll remember that in the last video we said the amount of heat needed to raise the temperature of a mass m through an amount delta T was given by this formula. So as we add heat, the temperature of the material changes. But here and here, where we're either going from solid to liquid or liquid to gas, the heat we add doesn't change the temperature. So the term latent heat simply means it's kind of hidden. In other words, as we're adding heat, the temperature is not changing, versus once we're in this range or down here, as we add heat, the temperature changes, as we talked about in the previous video. Here are some heats of fusion and vaporization, and the one thing you'll notice is water is kind of unique in that within the everyday temperatures we experience, we see water going from solid to liquid or liquid to gas. There are other materials that you're familiar with that you probably only think of in one phase. For example, nitrogen and oxygen, the two most common elements in the atmosphere, we think of those as only gases. But oxygen and nitrogen can be in liquid form or even solid form if we cool them down enough. You'll notice the boiling temperature for nitrogen, in other words, the temperature it becomes a gas, is minus 195 degrees Celsius. So to turn nitrogen into a liquid, you'd have to cool it below that value. To turn nitrogen into a solid, you'll notice you'll have to cool it down even more. So obviously those are very low temperatures, which is why in everyday life nitrogen is only found as a gas. If you've ever had something like a wart burned off or some other cosmetic procedure, you might have noticed that they use liquid nitrogen to freeze the wart off because liquid nitrogen is so cold. And you'll also notice that you can see it turning into a vapor during that process. On the other end of the scale, we have metals which we're not used to seeing in liquid form. So if you think of a gold ring or a silver ring, we don't think of those as being able to be a liquid or a gas, and that's because the melting point is so high for most metals. And so we have to heat them up quite a bit to turn them into a liquid or turn them into a gas even more so. Here's just a quick concept check question. I heat water on the stove until it begins to boil. After it has been boiling for 5 minutes, what's the temperature of the water? Well, hopefully you've all yelled at your screens that it's still 100 degrees Celsius, because as long as we have water and steam simultaneously, we know the temperature is still 100 degrees. In other words, if you put a thermometer in your boiling water, it's never going to read more than 100 degrees. Let's try a sample problem. How much energy is required to completely melt 2 kilograms of ice that starts at a temperature of -5 degrees Celsius? The heat of fusion of water is 3.33 times 10 to the 5th joules per kilogram, and the specific heat capacity of ice is 2090 joules per kilogram degrees Celsius. Well, the first thing we want to do is just kind of conceptualize the problem. And to do that, let me bring up a piece of that graph that we've been showing. So notice that we're starting at a temperature of -5 degrees. So we're starting right here. So you'll notice the first thing we have to do is add a certain amount of heat just to get the temperature from -5 to 0. So I'll call that Q1. Then we have to add another amount of heat, which is the heat required to take that ice and turn it completely into a liquid. We'll call that Q2. So we got to do two separate things. You'll notice the first thing we're going to do is what we worked on in the last video. In other words, Q1 is just going to be equal to mc delta T, because that's the heat required to change a certain amount of a substance by a temperature delta T. Let's look at delta T here just to be a little bit careful of this. We're starting at -5, so you can probably right away see that we need to change the temperature by +5 degrees Celsius. But let's just look at that mathematically. Remember that delta always means final minus initial. So the final temperature that we want to get to is 0 degrees. The initial temperature is -5, but we're subtracting -5 degrees. And so minus a minus is a plus. And so delta T is +5 degrees. Okay, so now we can plug in our values. Q1 is equal to the mass, which is 2 kilograms, times the specific heat capacity of ice, since that's the material we're dealing with currently, is 2090, and then delta T is 5. If you plug that into your calculator, you should get that Q1 is equal to 20900 joules, or 20,900 joules. So that's how much energy it takes just to warm the ice up to the freezing point. But now we've got to figure out how much energy does it take to fully melt that ice, and that's Q2. So now we're using our new formula here, that the amount of heat required to melt a quantity of ice is going to be the heat of fusion times the mass that we're trying to melt. So here we have the heat of fusion, which is 3.33 times 10 to the 5th. That's joules per kilogram, and we're going to multiply by the number of kilograms we have, which is 2. So you'll notice what we get is 66 or 666,000 joules. And that's Q2. To finally answer the problem then, we just have to bring our two answers together. So we know that the total heat that we're going to have to add is just equal to the total we had to put in to bring the ice up to 0 degrees plus the amount to actually melt the ice. And we had 20,900 joules, and we're adding 666,000 joules to that. And what we get then is 686,900 joules. Why don't we just go ahead and put that in scientific notation? And since we only had 2 digits in most of the numbers that we put in, we'll want to only have 2 digits in our answer. Therefore, the total heat that was added, let's see, 1, 2, 3, 4, 5, would be 6.9, so I'm rounding to 6.9, times 10 to the 5th, and that would be joules. So that's the total amount of energy to take that ice from -5 degrees and turn it completely into water. So we calculated the heat for that part plus the heat for that part. The heat of vaporization looks just like the heat of fusion. It's the same equation. We're just changing the subscript there. So again, heat is in joules. Since we know that mass is in kilograms, we want our heat of vaporization to have units of joules per kilogram, just like heat of fusion. Well, let's go ahead and do a problem. This might actually be a good time for you to pause the video and see if you can do this one yourself, and then restart the video and see if you got it right. How much energy is required to completely boil away 2 kilograms of water that starts at 22 degrees Celsius? The heat of vaporization of water is 2.26 times 10 to the 6th joules per kilogram. The specific heat capacity of water is 4,184 joules per kilogram. Let's look at it conceptually first. You'll notice that this time we're starting somewhere down here. Remember, this is 0 degrees. That's our melting. We know up here is 100 degrees. And so we're starting somewhere here. And the first thing we have to do then is add enough heat to get that water up to 100 degrees. And so the amount of heat required to do that we'll call Q1. And then the amount of heat we need to add to turn that water entirely into a gas or vapor is going to be Q2. So very similar to the way we approached the last problem. Let's start with figuring out Q1. That's going to use this equation because that's the amount of heat to change the temperature of a substance. So we've got mc delta T. And again, let's just look at delta T. Notice that the final temperature is 100. So final minus initial, which is 22. And you'll notice that what we get is delta T is 78 degrees. So that's what we're going to want to plug in for delta T. The mass is again 2 kilograms. The specific heat capacity of water is 4,184. And the delta T we're putting in, as we just figured out, is 78 degrees. If you calculate that, what you should get is that Q1 is equal to 652,704 joules. So that's the amount of energy it takes just to warm the water up from 22 degrees Celsius to 100 degrees Celsius. Now the next thing we want to do is figure out how much energy it takes to turn all of that water into a gas. And that's going to be using this formula. That's what we're calling Q2. So that's just the heat of vaporization times the mass. And the heat of vaporization given here is 2.26 times 10 to the 6th. And we want to multiply that again by our mass of 2 kilograms. When you calculate that, you should get 4,520,000 joules. So that's Q2. And now again, we just need to put those answers together. So we had Q1 is equal to 652,704 joules. We had Q2 is equal to 4,520,000 joules. And we know that the total heat that we're going to have to add to get our 22-degree water all the way up to completely vaporized is going to be the total of Q1 and Q2. And so when you do that math, you should get 5,172,704. And obviously that's a lot more digits than we really need since we only had our input data to a couple. So let's change that to scientific notation and round it off. So 1, 2, 3, 4, 5, 6. So we've got 10 to the 6th, and then we'll round that to 2 digits. So that would be 5.2 times 10 to the 6th joules. And that's our answer. By the way, obviously we can do these calculations in reverse as well. In other words, you could say how much energy does water vapor have to lose to become fully water, and then how much more would it have to lose to cool off. It's really the same thing. We're just looking at the heat that the substance has to give up as opposed to the heat that we have to add if we want to raise the temperature or boil it. That's all for this video. In our next video, we'll look at how heat is transferred, and we'll talk about conduction, convection, and radiation.